right, well, can I have everyone's attention? All right, let's just get started. I don't know where people are at, but okay. So today we're going to finish chapter 6, right on schedule, and then we're going to start chapter 7. Chapter 7 may be one of my favorite chapters because it's very, I don't know, it's like a quantum leap. It's very cool. All right, so we'll finish chapter 6, which I also like a lot. So, okay, so in chapter 6, we've gone through all this stuff: thermochemistry, energy. We've been talking about the first law all the time. Internal energy, heat, and work. We talked about that. Calorimetry. We talked about that. 2 kinds of calorimetry: bomb and coffee calorimetry. So today we're just going to finish this last leg of chapter 6. All right. Okay, so we'll do Hess's law. We'll talk about heats of formation and standard enthalpy. All right. So last time when we were doing enthalpy, we were talking about. I do not at the moment have.
It's okay.
Yeah, I'll have to. Okay, so we were talking about thermochemical equations. Okay, these are some examples. So if you take carbon burning and oxygen to produce carbon dioxide, it has an enthalpy associated with it. Is this exothermic or endothermic? Are we paying attention? We are not paying attention. Why not? All right. So, is this enthalpy exothermic or endothermic? Exothermic. Why do we say exothermic? Because it's producing heat. How do we know it's producing heat? What tells us it's producing heat? Negative. The negative sign, right? The negative sign tells us that this system, which is the reaction of carbon burning with oxygen, is releasing heat. It's negative. So this is an example of a thermochemical equation. Now here's the thing. If you double the amount of carbon burned, you should double the amount of heat released. That should make sense, right? So one of the properties of thermochemical equations is that if you double the amount, you double the enthalpy. Okay, so this is the example. If you triple the amount, you would triple the enthalpy. Now here's another one, another property of thermochemical equations. What if you went backwards? What if you took carbon dioxide and made it somehow go back into usable carbon and oxygen? Like I said, if you could ever find a way to do this without an energy input, you come talk to me. I'll be your best friend because you'd be a very, very wealthy person. Even wealthier than Jeff Bezos, founder of Amazon. So anyway, if you reverse this equation, okay, what happens to the sign of the enthalpy? It goes from negative to positive, right? So to put carbon dioxide back into usable carbon and oxygen, you have to have that same energy input to go back in. Where would this energy come from? All right, I'll tell you where it come from. You'd have to burn more and more fossil fuels just to drive this back to being usable carbon. That makes no sense because if you're using fossil fuels to drive this backwards, you're using more carbon. It just doesn't. It's not solving the problem. It's actually making it worse. You're producing more carbon dioxide to take carbon dioxide out of the air. That doesn't make any sense. Okay, so so if you reverse a reaction, the sign of the enthalpy changes. Okay, and then another property of thermochemical equations, we call it Hess's law. And what Hess's law says is that if you add up all of the enthalpies of reaction, and if you add them all up for a series of reaction steps, for the overall reaction from those steps, you would get the overall enthalpy if you added all the delta H's together. All right, so that'd be Hess's law. So here's an example. So so we take the formation of N2O4 from NO2, and you're given these 2 reactions. How do you figure out what the enthalpy is for this? So in other words, you're given this reaction, you're given this reaction, you're given these delta H's, okay, but how do you get delta H for this reaction, is the question. And so the idea is that you have to add up these reactions to get your desired reaction. So let's do that. So if you're going to add these up, let's look at what we have. For the desired reaction, we want N2O4 on the product side. Is N2O4 out of these equations, is it already on the product side? The answer is yes. Okay, so we're good there. We need NO2 on the reactant side. Do we have NO2 on the reactant side? And the answer is no, we don't. So what we're going to have to do is we're going to have to flip this first reaction around in order to make NO2 on the left side of the arrow. Right, so we'll do that. So writing reaction 1 backwards, okay, and we get N2 plus 2O2. What is the delta H of that reaction? It's going to have to be negative, right? You're going to flip the sign. So this is now negative 66.4 kilojoules. And then for the second reaction, we can leave that the same. Okay, because of the fact that we already want that on the right side. So if we add these two reactions up now, we should get the reaction at the very, very top there. So do we have, can we cancel out these two O2s here? And the answer is yes, we can do that. All right. Think of the arrow, we call these chemical equations for a reason, because the arrow really is an equal sign. All right. So when we add these up, we can cancel those. We can also cancel out the nitrogen molecules. And so what we end up getting is 2N2O. And that gives us N2O4. What is delta H for this reaction?
5.3.
Yeah, it's negative, right, negative, adding negative 66.4 to 11.1, you get negative 55.3 kilojoules. All right, and that's Hess's law. Okay, so Hess's law says that we can add up a series of reactions to get the desired reaction, and we can get the enthalpy of reaction for our desired reaction by adding the enthalpies of the individual steps. Right, that's what Hess's law tells us. It's really not that hard. It's actually, these are nice problems to do, but it does require a little bit of just observing what you need to flip around. It might be a situation where you might need to multiply some of these through by some factor to get rid of things. And we'll get a lot more practice with this as we go into other topics. Okay. All right, questions? Okay, so let's do another one. So as it says, calculate the enthalpy change for the combustion of C2H2 from the formation reactions below. Okay, so this one doesn't give us the desired reaction, we have to come up with it. So what is our desired reaction? By the way, I just caught a typo here. This negative 285.8 should be negative 241.8, sorry. There we go. Just change that to. Alright, so it should be negative 241.8. Okay. Okay. So let's do this. Any ideas of where to start? So what is it? So we have to have two things. We have to have a set of reactions, but we also need to have a desired reaction. But we don't have that. But can we get it? Can you write a combustion reaction for C2H2? And what would that be?
C2H2 plus oxygen.
Right, C2H2 plus oxygen.
Produces CO2 water.
Right, produces CO2 and water. Okay, and then we have to balance this. So let's see, C2, we got 2 carbons there, 2 hydrogens already, we got 5 oxygens. So what this ends up becoming is 5 halves, but getting rid of the half, we get four and 2. All right, so just double check that we balance things. All right, so 4 carbons, 4 carbons, 4 hydrogens, 10 oxygen, 8 plus 2 gives me 10 oxygen. All right, so there's a balanced reaction. This is what we want to get, and the question is asking us, what is delta H for this reaction, given these other reactions here? So, any other ideas on what to do from here? So right now we've got what, 4 carbons, excuse me, not 4. Right now as it is we have 2 carbons plus H2, and that gives us C2H2. And we also have C plus O2. And we also have H2. Plus half an oxygen gives us water. Okay, so how can we add up these reactions? How can we add these up to get us what we want? What was that?
Oh, we flipped the first one.
Right, you gotta flip the first one, right? Because we want C2H2 on the left side of the arrow, but right now, the only reaction with a C2H2 in it has it on the right side. So we're gonna have, right now it says delta H for that reaction is 227.4, positive 227.4, but it's now going to become negative 227.4. And when we change that to a negative, we reverse this. So now it's going to be C2H2 going to 2 carbons plus hydrogen. All right. And then of course this would was still negative 393.5. This was still negative 241.8. Okay, is there anything else we could do from here? So we have 2 carbons here. Do we have any carbon in this reaction at all? Like any carbon by itself? We don't, right? So we need to somehow cancel out the carbon. We also need to cancel out the hydrogen gas as well. So how can we get rid of the carbon? What if we multiplied, what if we did this? What if we multiplied this whole reaction here? What if we multiplied it by 2? Okay, what would we get? All right, so we ended up getting the new subscripts would become 2 and 2 and 2, and this would also be times 2. All right. So at that point, can we quite get this? How many CO2s do we have in this reaction? We have 4, right? So actually, we need to get 4 CO2s in our products. So is multiplying by 2 going to get us there? And the answer is no. So we're actually going to have to multiply through by 4. So it's not just about canceling things, you got to look at what you have in your desired reaction. So this becomes 4, 4, and 4. All right, now we're cooking. I use the word cook because we're doing lots of exothermic reactions right now. Okay. So we have 4. We have our 4 here. Can we get our 2 somehow? We can, right? So what about multiplying the bottom reaction by 2? That gets us 2 there. Also, multiplying by 2 here gets rid of that half. And so this becomes just simply a 1. And there's a 2. And there's a 2. And what else can we do? So we have our 2 waters, we've got our 2 carbon dioxide, our 4 carbon dioxide. We need to cancel out the carbon and the hydrogen. So what do I need to do to the top reaction? Multiply that by 2 as well. Alright, we'll end up getting 2 there, which actually matches the 2 for our balanced reaction for C2H2. This becomes 4, and this becomes 2. So we had to do a lot to this one, a lot more than the first one, right? We had to come up with a reaction, right? Can you write a combustion reaction from a hydrocarbon burning, and remember that it reacts with oxygen, remember that it produces CO2 and water, balance it, and then on top of that, can you see then how you need to flip reactions around and multiply through by certain factors to get what you want. So let's add these reactions up. Okay, we end up getting grand total. Okay, we get 2C2H2. Alright, the 4 carbons will cancel. The 2 H2s will also cancel. If I add 4 plus 1, that gives me 5 oxygen. And I get my 4 CO2s and I get my 2 waters. What is delta H, is the question. Alright, so what is delta H? So if you multiply this times 2, this times 4, and that times 2, add them all up, what do you get? So let me write this out. So you got 227, negative 227.4 times 2 plus negative 393.5 times 4 plus another negative 241.8 times 2. So that ends up equaling, you should get something like negative 2,512.4 kilojoules. Anybody else get this? Something like that? All right. How do you feel about Hess's law? It's like a puzzle. Anyone like to do puzzles in here? Anyone like to play Sudoku or something like that? I love Sudoku. All right. And these are fun to do because they're kind of like a puzzle. You just have to see, okay, what chemistry do we have? And then how can we add up these other reactions given to us to produce the reaction that we want? Okay, and so it involves either flipping reactions around, which in that case you need to remember to change the sign, or it involves multiplying through by some factor to get rid of unwanted reactants or products, but also to match the coefficients in your balanced desired reaction. Right, so Hess's law is kind of fun. They're not hard, but it is like a puzzle. So it's a little bit like Sudoku in that regard. All right, any questions about Hess's law?